Hello, everyone. Today, we will study Module 4, the core task in PLC system design for sequential control systems. Task 2, design and simulation of an automatic door control system. Next, let us clarify the core requirements of this task. The essence of automatic door control is sequential control of motor forward and reverse rotation. The key rule is stop before switching. There are two specific scenarios. First, press the forward start button SB1 and the motor runs forward. You must press the stop button SB0 to stop the motor, before pressing the reverse start button SB2 to run the motor in reverse. Finally, press SB0 again to stop the reverse rotation. Second, first, press SB2 to run the motor in reverse. Likewise, you must press SB0 to stop it before pressing SB1 to start forward rotation. In short, forward and reverse rotation cannot be switched directly. The stop step is mandatory. In this task, we set objectives from 3 dimensions. First are the knowledge objectives. Understand the concept of sequential control systems. Master the drawing of state transition diagrams. Understand the programming application of PLC step sequence control. Further become familiar with debugging methods in TIA Portal. Next are the ability objectives. Be able to independently write simple sequential control programs, and complete program design and simulation debugging using the set or reset sequential control method. Finally, the quality objectives. Cultivate dialectical thinking and inductive ability. Enhance teamwork and innovation awareness. Establish engineering awareness, such as safe production and quality consciousness. Learn to collect information through online resources, and cultivate the spirit of excellence and correct values. Now we will study the core-related knowledge. The set or reset sequential control design method. First, let us look at step activation. Each operating stage of the system is called a step. It is represented by PLC bit memory M, such as M0.0, M0.1. The step activation logic is as follows: when the previous step, such as Mi-1, is active and the transition condition, such as a push button or timer signal SHI, is satisfied, the current step, Mi, is set and activated. At the same time, the previous step is reset. This is like a relay race. Only after the previous runner finishes and passes the baton can the next runner start. Please understand this in combination with the diagram on the screen. Previous step Mi-1, transition condition SHI, current step Mi, next step Mi+1. This logic enables sequential progression. This is the core principle of sequential control. Next, let us look at output actions corresponding to steps. When a certain step, Mi, is activated, it triggers the corresponding output action, Yi. For example, when the motor forward step, M01, is activated, it drives output Q0.0, the forward contactor. The motor runs forward. When the step is reset, the output also stops accordingly. We must also focus on emergency stop handling. In emergency situations, the emergency stop signal must immediately reset all active steps and cut off the outputs to ensure the safety of equipment and personnel. This is a mandatory safety design in industrial control. Now we move on to the task implementation stage. The first step is I/O assignment. Determine the correspondence between hardware components and PLC addresses. This is the basis of programming. Please look at the I/O assignment table. Input side, the forward button somebody 1 corresponds to I1.0. The reverse button somebody 2 corresponds to I1.1. The stop button somebody 0 corresponds to I0.5. Output side, the motor forward contactor coil KM1 corresponds to Q0.0. The reverse contactor coil KM2 corresponds to Q0.1. Be sure to remember these correspondences clearly. They will be used directly in subsequent programming. The second step is to draw the workflow diagram. This visually presents the control logic. The initial state is the initial step, M0.0. First, press the forward button, I1.0, to enter the forward step, M0.1. Output Q0.0 is energized, motor runs forward. Press the stop button, I0.5, to return to the initial step. Second, Press the reverse button, I1.1. Enter the reverse step, M1.1, output Q0.1 is energized, motor runs in reverse. Press I0.5 to return to the initial step as well. The flowchart clearly reflects the rule of stop before switching. There is no direct forward to reverse or reverse to forward path. The third step is to draw the sequential function chart. This is the blueprint for sequential control programming and consists of 4 steps. First, define the steps. Divide the control process into the initial step, forward step, and reverse step. Assign a PLC control bit to each step, such as M0.0, M0.1, M1.1. Second, draw the directions. Draw arrows along the progression of steps to define the sequence. Third, label the elements. Use PLC elements to represent the steps and transition conditions. For example, I1.0 is the transition condition from the initial step to the forward step. Fourth, define the actions. Determine the output action for each step. Represent them using PLC instructions. For example, the forward step corresponds to set Q0.0. The fourth step is to convert the sequential function chart into a ladder diagram. This is done in 4 key stages. First, initialization section. Use the PLC first scan system bit to set the initial step M0.0. This allows the system to automatically enter the initial state after power up. Second, transition section. For example, from the initial step M0.0 to the forward step M0.1. 2 conditions must be satisfied simultaneously. M0.0 is in the active state, normally open contact closed. The forward button I1.0 is pressed, transition condition satisfied. Then use a set instruction to activate M0.1. Use a reset instruction to deactivate M0.0. The transition logic for the reverse step is exactly the same. Third, output section. Use the step control bits to drive the outputs. For example, when the normally open contact of M0.1 forward step is closed, it drives Q0.0 forward contactor. When M1.1 reverse step is closed, it drives Q0.1 reverse contactor. Fourth, combination and optimization. Here, we may encounter the issue of multiple coils driving one output. That is, the same output appears in different program segments. The solution is to connect all driving conditions of the same output in parallel. For example, write the driving logic of Q0.0 only once and connect the relevant logic of M0.1 in parallel. This avoids program errors. Finally, let us summarize and extend. First, the key principles for drawing a sequential function chart. The transition symbol at a sequence branch point must be drawn below the horizontal line. The transition symbol at a merge point must be drawn above the horizontal line. This ensures that the sequential logic remains clear. I will leave you with 2 questions to think about. First, for branch and merge points in a selection sequence, how the ladder logic should be implemented specifically. Second, if a parallel sequence is involved, how should the sequential function chart be drawn? You can explore these questions further after class based on today's content. That concludes today's lesson. Thank you for your attention.